The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Last week we talked about the key components of a proof: propositions, axioms, and logical deductions. And as you probably talked about during recitation, we're not going to worry too much about what axioms or logical deductions that you use. Anything that is reasonable is fine by us. We're not going to ask you to know what modus ponens is or to label some law when you make a logical deduction. Just, be reasonable. Any fact you knew coming into this course about mathematics, probably close enough to use as an axiom. You want to make sure your axioms are consistent, but that's OK. Now, the exception to this would be, say we're on an exam and we ask you to prove some proposition P. Well, you can't say, I already knew P, it's an axiom, check. That's not so good. We're asking you to prove it from some more elementary facts. OK, it's also, you don't want to be making wild leaps of faith or saying it's obvious that unless it really is obvious. That kind of stuff can get you in trouble. Much better to sort of explain the reasoning in the proof. Now, the proofs that we covered last week in recitation and the problem set were all examples of what are called direct proofs. You start with some axioms, you have some theorems you knew before or you proved along the way, and you make logical deductions until you get to where you want to go, the theorem. We're going to start today with an indirect proof. For example, a proof by contradiction. And this is a little bit different. In a proof by contradiction, you assume the opposite of what you're trying to prove. Then you just take steps forward, logical deductions forward, until you arrive at a contradiction, something where you prove false equals true. Now, if you can ever get to the point where you prove something is false and true, that means what you assumed at the start had to be wrong. Namely, that what you're trying to prove has to be true. So let's write that down, because it can be a little confusing the first time. So to prove a proposition P is true, you will assume that it's false. In other words, that not P is true. And then you use that hypothesis, namely that P is false, to derive a falsehood. In other words, you prove a falsehood is true. And this is called deriving a contradiction. And so it must be that, in fact, P is not false, namely that it's true. Now, this works because if you can prove if not P implies false is true, well, from last time, the only way this is a true statement is if this is false, namely P is true. All right, so we can conclude that P is true if we can show that not P implies a falsehood. Any questions about that? Is sort of a lot of sort of notation, and until you've seen it, it can be confusing. So maybe we should do an example. Let's prove that square root of 2 is irrational. Is irrational. OK, everybody knows what an irrational number is? That's something that can't be expressed as the ratio of integers. OK, and probably most people already know that. How many people have not seen a proof that square root of 2 is irrational before? All right, so most of you have seen a proof of that. Good. You know, if you try to do a direct proof of this, it's pretty hard. How do you show there's no way to represent the square root of 2 as integers a over b? But it's very easy if we do a proof by contradiction. Now, when you're doing a proof by contradiction, always start off by saying by contradiction. Write that down. And then what you do next is you say, I'm going to assume, for the purpose of contradiction, that that p is false, namely not p is true. In this case, that would be square root of 2 is rational. So in this case, here's what we're trying to prove. That's p. I'm going to assume not p, namely that square root of 2 is a rational number. Then I'm going to get a contradiction or a falsehood, and then I'm going to know that p was true after all. All right, so let's see where this leads us. Well, if square root of 2 is rational, then we can express it as a over b, where a over b is a fraction in lowest terms. That means a and b have no common divisors. And then I can square both sides. And I get 2 is a squared over b squared. Then I multiply by b squared, and I get 2b squared equals a squared. And what does that imply about a? What can you tell me about a if a squared is 2b squared? Anything special about a? Can a be anything? A squared is even, right? Because 2b squared is an even number, so a squared is even. And what does that mean about a? A is even. If a squared is even, then a is even. So a is even. All right, so we can write that as 2 divides a. That's the divide symbol. You'll see a lot of that next week. All right, if a is even, what do I know about a squared? I know more than just it's even. What is it? It's a multiple of 4, yeah. So that means that 4 divides a squared. A squared is 2b squared, so that means that 4 divides 2b squared. Divide each side by 2 means 2 divides b squared. What does that imply about b? B is even. All right, b is even. Good. Well, I've got a is even and b is even. Have I got a contradiction here somewhere? Yeah, a over b was not a fraction in lowest terms because both a and b are even. All right, so that implies a over b is not in lowest terms. And that gives a contradiction. Now, you'll see that written lots of ways. One is you can say a contradiction. Sometimes you'll see just this sharp symbol written. And that means you got to a contradiction because here we had it being in lowest terms, and here we have it not in lowest terms. You can't have both at the same time. So you got a contradiction. And that means we've now proved that this assumption was wrong. Square root of 2 is not rational, so it must be irrational. All right, and then we put a little box here at the end, or sometimes you'll see a check, sometimes you'll see QED that says the proof's done now. It's over. Any questions about that proof? We're going to do a lot of proofs by contradiction. Actually, there's an interesting story behind this proof. As far as we know, it was first discovered by the Pythagoreans way back when in ancient Greece. And the Pythagoreans were a religious society started by Pythagoras of Pythagoras theorem fame. Now, it sounds weird today, But back then, in ancient Greece, math was a religion. All right? Every once in a while, you'll see somebody around MIT, and you'll think, he must think math is a religion. But back then, it really was, and it was ruled by gods, because this is ancient Greece. And there were two key gods in this religion, Aperon and Peros. Now, Aperon was the bad god, and he was the god of infinity, because infinity was considered all that was bad. And I don't think we'll do a lot with infinity this term, but if we do, you'll appreciate why that's the case. And Peros was the good god. He was the god of the finite world and represented everything that was good to the ancient Greeks. Now, one of their main axioms or beliefs was that there were no irrational numbers. They just didn't exist. Now, the reason is they didn't like irrational numbers. They were bad because, well, they're infinite. You can't write them as a decimal without repeating forever. And, just an infinite sort of decimal representation. They liked rational numbers, like 1/7. That's a good number because you can write it as 0.142857 repeating. So rational numbers are finite in that you can always find the repeating pattern of finite length. Irrational numbers are not. They're infinite in that sense of the ancient Greeks. So they said there were no irrational numbers. That was an early axiom. Now, they also had an axiom that said that every length of a line was finite, therefore rational. All right, the ancient Greeks were good with the compass and drawing lines and straight edges and stuff. So they said any line that you can construct has a finite length to it, so therefore it has a rational length. That was axiom number 2. Now, they were good geometers, so they knew, of course, they developed the Pythagorean theorem, that if you took a triangle and you had side lengths 1, the length of the hypotenuse was square root 2. Therefore, they had a theorem that said square root 2 was rational, because you got the two axioms there, right? Now, eventually, they discovered a proof like that it wasn't rational. It was irrational. Now, this caused quite a stir. First, it meant that their axioms were inconsistent. Every theorem they'd proved was now suspect once you have inconsistent axioms. Even worse, the devil is in their midst. Square root 2 is infinite, is the bad god, and this is the most basic length they had, besides 1. All right, so that's a very bad thing. Sort of like, today we were to wake up and discover that, there were only 9 commandments, and the 10th was planted there by the devil, and you're not sure which one maybe. That would be a big mess, sacrilege. Well, so what were they to do? This is a disaster of major proportions, so they covered it up, and they denied the result. So they didn't want to publish that proof. So they kept on saying square root 2 was rational. But then, according to legend, there was a deep throat. Somebody who let out the word and the proof that square root 2 was irrational, because that would be very destabilizing for the society. And so they killed him. This is the legend. Now, hard to imagine getting killed over the irrationality of 2, but all right, we're going to do a lot more of these kind of proofs in homework and throughout the term. The next proof I want to show you is one of my favorite proof techniques, one of my favorite proofs, and that is a false proof. And we're going to see a lot of these during the term too. And if we could bring the screens down, somebody back there to, yeah, great, bring the screens down, and then turn this on for me. So I'm going to prove to you that 90 is bigger than 92. All right, and that hopefully is not really true. But watch this proof and see if you can see any problems with it. All right, the proof by PowerPoint. Right away, you should be suspicious. I'm going to take 2 triangles with total area 90 and put them together and then divide them up into 4 triangles with area greater than 92. And by the conservation of area axiom, which you want to be maybe thinking about, this will imply an area of 90 is larger than an area of 92, and therefore that 90 is bigger than 92. All right, those are my triangles. They are right triangles, 9 by 10. If I put them together, I get a 9 by 10 rectangle. Of course, it has area 90, 9 times 10. now I'm going to slide these triangles across their diagonal so that I get, instead of having 10 on the side, I'm going to slide it so I get a 2 and an 8. Okay? I had 10 there before, now it's 2 and 8. And then you see I've got this, I'm going to cut off along the dotted line. And as you can see, that dotted line, won't compute it exactly, but it's a little bit bigger than 2. Right? It's a little bit longer than that 2 there. You can see that. All right, so I'll call it 2 plus, bigger than 2. Now I slice off along the dotted line. And now I'm going to put those two triangles together, and I create a rectangle, 2 by 2, a little more than 2. Now the area of the little rectangle is bigger than 4, because I got 2 times something bigger than 2. And you can see here I have the 8 left over, and I have 9 plus 2 plus means it's a little bit bigger than 11 by 8. I got area bigger than 88. Add them up. I got area bigger than 92. So I started with 90, and I created more than 92. All right, what's the problem here? I mean, this would be good if I could do it. I'd get some gold, bars of gold and, cut them up and do the game, and I'd make more gold. That would be pretty good if I could do that. Is it the conservation of area axiom? Did I assume something there that was too powerful, that if I manipulate the area of rectangles like this, that the area needs to be the same? Yeah? My bigger ones aren't closed. Well, let's see. I don't know. Let's go back and see how I made those bigger ones. All right, I got my triangles, right? I'm just chopping along the line there, and I got 2 plus and 9. Those are rectangles. They look like rectangles. Yeah, yeah. Well, it looks bigger than 2, doesn't it? Yeah, 2 plus is, well, bigger than 2 is bigger than 2, but yeah, maybe that should have been a 2 minus. Would that change anything? Yeah, if that had been a 2 minus, then we'd have area less than 4, area less than 88, and then 90 would be less than 92. That would be okay. But it sure as heck looks bigger than, the 2 plus looks bigger than the 2, doesn't it? I don't know. Do they got distortion out there? I guarantee you if I measured on my screen, that 2 plus is bigger than the length of the 2. I guarantee you. We can take a ruler on my screen, and the 2 plus will be longer on the ruler than the 2. That I guarantee you, but you're on the right track. Yeah?
That 2 plus is really 1.8.
Good. All right. Now, how did you? But it is true. If I measure it on my screen, it's bigger. Yeah.
So are the triangles like drawn to scale? It's like on
No.
the SAT they always say not to scale, right?
Yeah. Yeah, they're not drawn to scale. In fact, if I go back to the beginning, it says 9 by 10. But in fact, if I measure the 9, it's bigger than the 10. All right? So this is one of the big problems of proofs by picture. Because looking at it, you're not thinking which is bigger, 9 or 10 up there. The 10's bigger, even though it's not. It's shorter. But when you get down into the proof, well, clearly the 2 plus was bigger than the 2, because it looks that way. It is on the paper. All right? In fact, if you go computer, you're probably right. It's 1.8, not 2 plus. But that's how the error crept in and how it was drawn. And then you're going along with the proof, and everything else is just fine. So the mistake is right up front. I drew it wrong. Okay? And this happens, you're doing graph, we'll talk about graph theory in a couple weeks, over and over again, people do this. They draw it. It looks like this, you accept that, and then you're dead. Everything else, there's no hope. Everybody clear what went wrong in this picture? How we got off track? That's sort of a nasty one. Okay. Now, one of the nice things about proofs is that when there is a bug, if you really write it out step by step, and there's a bug, you can go back and find it. And so this, I didn't sort of really write it out very well step by step, and it was harder to find. Now, all right, so if we can pull the screens up. Thanks. Okay, so for the rest of today and the rest of this week, we're going to talk about a different kind of proof technique, which is induction. Now, induction is by far the most powerful and commonly used proof technique in computer science. If there's one thing that you should know by the time you're done with this class, it's how to do a proof by induction. In fact, if there's one thing you will know by the time we're done with this class, is how to do a proof by induction. And in some sense, when we get to grading the final, how we measure ourselves as instructors, the first test is, can you do the proof by induction question and do a good proof there? You will see it on the midterm and the final, probably in multiple instances. Now, just to make sure you become intimately familiar with induction, we're going to do over a dozen proofs with induction in class and many more in homework over the next 5 to 6 weeks. You'll probably be dreaming about induction if we're successful here soon. The good news is that induction is very easy. Once you get your mind around it, get some practice, it really is not a hard thing. In fact, induction is really just an axiom. So let me state it. Let Pn be a predicate. If P of 0 is true, and for all natural numbers n, P of n implies P of n plus 1 is true. So here I'm saying that this is true for all n. Okay. Then, for all n natural numbers, P of n is true. All right, another way of saying this without the for alls there is that if P0 is true, if P0 implies P1 is true, if P1 implies P2 is true, and so on forever, then P of n is true for all n. So then P0, P1, P2 forever are true. Okay? Now, you can sort of see why this is a reasonable axiom. Because if P0 is true, and P0 implies P1, then by that modus ponens thing, or one of the logical deductions, we know P1 is true. And if P1 is true, and P1 implies P2 is true, then we know by the same reasoning P2 is true. And so on forever. Now, the reason it becomes an axiom is that and so on forever part of it. That's why we need it as an axiom. You can sort of view this as a series of dominoes. You know, I got a domino for each n. And each domino knocks over the next in terms of truth. Knocking over corresponds to truth here. And if I know P0 is true, that means I knock over P0. P0 implies P1 means P1 goes down. P1 implies P2 means P2 goes down, and so forth. All right, pretty basic. Raise your hand if you think you don't have a lot of experience with induction. All right, yeah, that's pretty typical, about a third to a half of you. So we're gonna change that. Let's do a simple proof using induction. So let's prove that for all n bigger than or equal to 0, again, natural numbers, that 1 plus 2 plus 3 plus n equals n times n plus 1 over 2. This is actually a useful thing to remember. We're going to use this all term, this identity. Now, the first thing, before we prove it, I want to make sure we understand this this dot, dot, dot notation, because it is the source of a lot of errors. What it means is that you need to fill in the pattern here, which is vague. What it means in this case is you fill in 4, 5, 6, all the way up to n minus 1, and then n. That's what it means. Figure out the pattern and fill it in. Pretty risky thing. Now, in this case, because that's so vague, there's other terminology we use for this. For example, we would use a big sigma, capital sigma, I equals 0 to n of I. That means the sum of I, where I is the integers from 0 to n inclusive. Actually, let me put 1 here. Okay. Another way to write this, these are all equivalent ways to write it, is you could put 1 less than equal to I less than equal to n of I. So you could put summing I over the range from 1 to n, or you could write it on the bottom if you want. So these are 4 different ways of writing the same thing, the sum of the natural numbers from 1 to n. And we'll use them all during the term. All right, now there's some special cases that make this a little more interesting. What if n equals 1? I've got 1 plus 2 plus dot, dot, dot plus n. What do you suppose it equals if n equals 1? 1, because we're summing the numbers from 1 to 1. That's just 1, the number 1. There is no 2. And there aren't 2 copies of 1. So this notation is very ambiguous. You see a 2 here in the sum. If n is 1, you see a 1 here and a 1 here. All right, so you've got to be careful. I guarantee you, you'll make a mistake with this. In fact, I'm going to show you another false proof later where this comes into play. What about if n is less than or equal to 0? What is it then? Any thoughts? 0. There are no integers to sum. No 1, no 2, no n, because you never get started because you're, sorry, n is less than or equal to 0. Because you're summing from 1 to 0, 0 is below. You never, doesn't include anything. So these are the conventions to keep in mind with the edge cases here. All right, it's easy enough to check that the theorem is true for certain values of n. For example, if n equals 4, I've got 1 plus 2 plus 3 plus 4. That's 10. And 10 equals 4 times 5 over 2, plugging in the formula. So for any value of n, you could check this formula is true. Proving it's true for all n, you know, takes a little more effort unless you use induction. So let's do that. So we'll prove the theorem. Now, whenever you're using a proof by induction, first thing you do is you write down by induction. So we know what you're going to do. And the next thing you need to do is figure out what's your predicate. What's your inductive hypothesis? What's P? All right, so usually P will be the thing you're trying to prove, namely that 1 plus 2 plus 3 up to n is n times n plus 1 over 2. And you state that. You say, let P of n be the proposition, the predicate, that the sum I equals 1 to n of I equals n times n plus 1 over 2. All right, and once you've got that established, now we're going to go verify that P0 is true and that n implies Pn plus 1. All right, so always have to write this down. The next thing to do is to check what's called the base case, P0. So let's do that. All right, so we write down base case. Some people call it the basis step. And we have to check that P0 is true. Well, what's the sum of I equals 1 to 0 of I? 0. There are no terms in this sum. And if I look over there, n times n plus 1 over 2, if n is 0, it equals 0. So we're done with the base case. We've now proved that P0 is true. And the second part is called the inductive step. And here we have to show, for n greater than or equal to 0, we need to show that Pn implies Pn plus 1 is true. Now, how do we show an implication is true? How do I show this is true? What am I going to do to show that's true in general? Yeah? Right, because an implication is true in every case except for true implies false. So if Pn is false, we're done. This implication is true. The only case we have to worry about is P of n is true. So we assume P of n is true, and now we confirm that that means Pn plus 1 is true. All right? So we write that down. Assume Pn is true. And you might also write down for purposes of induction or purposes of verifying the inductive hypothesis, just to let us know why you're assuming it. In other words, you're not assuming Pn is true for purposes of contradiction. You're assuming it for purposes of induction. All right, let's do that. So all right, that means, in this case, i.e., we assume 1 plus 2 plus up to n equals n times n plus 1 over 2. And we need to show that the n plus 1 case is true, namely 1 plus 2 plus n plus 1 equals n plus 1 times n plus 2 over 2. All right? You know, it's sort of weird, and this does confuse people that aren't familiar until you get familiar with induction. It looks like we just assumed what we're trying to prove. We're trying to prove this is true for all n, and we just assumed it. But we're assuming it in the context of establishing this implication is true. And then we apply the induction axiom to conclude Pn is true for all n. All right. Well, let's rewrite this as 1 plus 2 plus n plus 1. Because I've assumed Pn, I can rewrite this as n plus 1 over 2. And now plus n plus 1 out here. That equals, well, I got n squared plus n here over 2 plus 2n plus 2. All right, and that equals n plus 1 times n plus 2 over 2, which is what we're trying to show. So we've completed now the inductive step. We have shown that for all n, Pn implies Pn plus 1, for all n bigger than or equal to 0. Any questions about that? So the proof is done. We've done everything we need to imply induction. We got P0 is true, and Pn implies Pn plus 1 for all n bigger than or equal to 0. Now, induction helped us prove the theorem. Did it help us understand why the theorem is true? Do you have any feel for why the theorem is true after seeing the proof? Not really. No, I don't think, sometimes induction will give you an understanding, sometimes it won't. Here you got no understanding of why the theorem's true, which is sort of unfortunate. Did induction help you figure out the answer to the sum? Namely, say you were trying to derive this answer from this sum. Did induction give you the answer? No. You had to know the answer, namely this, in order to prove it was true. Now, later we'll see examples where induction actually can give you the answer, but often it does not. Often induction gives you no hints, no answer, just proves that it's right once you had the clever idea that, oh, maybe that's the answer. All right, and you'll see that with things like the beaver flu problem. All right, that figuring out the inductive hypothesis or the answer, the details of it is hard, but once you do it, then applying the induction, not so hard, but it gives you a concrete proof. Okay, let's do another one. In fact, we're just going to spend the rest of today doing induction proofs. Okay, so for all natural numbers n, 3 divides n cubed minus n. Means n cubed minus n is a multiple of 3. For example, n is 5. 3 divides 125 minus 5, because it's 120. Let's prove that. And we're going to use induction. What do you suppose Pn is going to be? What's my predicate or my inductive hypothesis here? Any thoughts? Yeah? Yeah, that's you. Go ahead. Yeah. First thing you always want to try is you assume that as your induction hypothesis. So we say let Pn be 3 divides n cubed minus n. What's the next thing we do in our proof? Base case. Always easy to forget, but not a good idea. Base case is n equals 0. And sure enough, 3 divides 0 minus 0. So that's done. What's the next step we do? What is it? Next step? Inductive step. And for that, we're going to need to show for n bigger than or equal to 0, we want to show Pn implies Pn plus 1 is true. So to do that, we assume Pn is true. In other words, we assume that 3 divides n cubed minus n. And we're trying to show that 3 divides n plus 1 cubed minus n plus 1. So we take a look at, we examine n plus 1 cubed minus n plus 1, and we want to show it's a multiple of 3. Well, let's expand that out. This is n cubed plus 3n squared plus 3n plus 1, and I subtract off n plus 1. So I get n cubed plus 3n squared plus 2n. Is this a multiple of 3? I need to show that's a multiple of 3, and then I'd be all done. Is it a multiple of 3? Beats me. It doesn't look like a multiple of 3 necessarily. So maybe we need to massage it a little bit. I do know that this is a multiple of 3. I can use that fact. And in proofs by induction, you always want to, if you're not making use of that fact, then you're not really making use of induction. Sort of a warning sign. So I want to use this fact to prove this. Well, let's get a minus n in here. This equals n cubed minus n plus 3n squared plus, well, if I subtracted an n, I got an add an n plus 3n. So I've rewritten it. Now is it clear? Now it's clear. Very simple, because 3 divides this by Pn, 3 divides that, and 3 divides that. So this is a multiple of 3. All right, because I've got 3 divides 3n squared, 3 divides 3n, and 3 divides n cubed minus n by Pn, or you could say by the inductive hypothesis. Pn is the inductive hypothesis, another name for it. So therefore, 3 divides that, which means 3 divides this. So that means 3 divides n plus 1 cubed minus n plus 1. And we are done with the proof by induction. Any questions about that one? So the key steps in induction are always the same. You write down proof by induction. You identify your predicate. You do the base case, usually at n equals 0, but it could be something else. And then you do your inductive step. Now, in general, you could start your induction, don't have to start it at 0. You could start it at some value b, some integer b. Let's take a look at that. So you could have, for the base case, you could have p of b is true, not p of 0. And then for your induction step, you would have, for all n bigger than or equal to b, Pn implies Pn plus 1. And then your conclusion is that for all n bigger than or equal to b, Pn is true. So inductions don't always have to start at 0. You can pick where you start. Just make sure that you verify the starting point and you verify the implication for all n at that starting point and beyond. All right, let's now do a false proof using induction. We're going to prove that all horses are the same color. Oops. So let's go through the process. So the proof we write down by induction. Now we need our induction hypothesis, the predicate. So